Hello, today we are going to look at how to solve exponential equations algebraically. So when we were talking about applications of exponential equations earlier, like with interest or money or how something was growing, a population, something like that, you did solve exponential equations at that point. Like I gave you a y value and you found out the x, you found the x that would make that true. But we did them with the graphs. We only had a graphic method of solving them at that point. But now that you know that logarithms are the inverse operation of an exponential, we will be able to solve them algebraically now. So that's what we're going to do today. I have three questions here for the three different levels that you'll see with exponential equations. So you want to ask yourself these questions. First of all, you want to check and see if your bases match. Because if your bases match, oh, this is going to be easy. Because if the bases match, the exponents also have to match. So that would look something like this in a problem. Maybe you would have, 5 to the 8th equals 5 to the 2x. So do you see how the bases are 5 on both sides there? If we have matching bases and these things are equal, well then the exponents must also be equal. You can think of the structure like this. Those match. So those must match if we're going to come out with equal answers. So this would mean that 8 equals 2x. Divide by 2 on both sides, and x equals 4. If you plug that 4 back in, you'll be able to tell that exponent becomes an 8. 2 times 4 is 8, so 5 to the 8th on the right side equals 5 to the 8th on the left side. Yep, it worked. Here's technically what's going on there behind the scenes. So let me get rid of all this extra writing. What we're doing here actually is we are going to take the log of both sides. Now, if we have a base 5, what log base do you think we should take? Yeah, let's take log base 5. Since they match, that's going to be super convenient. So I'm going to take the log base 5 of the left and also the log base 5 of the right. That's the fairness idea that we always see when we solve equations. You always have to be fair on both sides, so I'm taking the log of both sides, log base 5 of both sides. So now there was a property, one of the definition properties of logarithms that I want to call to your mind right now. It looked like this. We said that log base b of b to the m equals just plain m. So that's what we are using here. That's what we're going for. Can you see how my base is 5? My b would be 5 on both of those. So that would put the m on this side, the 8. So that means that all of this stuff is just equal to 8. When I take the log base 5 of 5 to the 2x, same thing happens. I would just be left with the exponent of 2x. So that's the hidden operation that we're doing on both sides there. So you're going to get 4. So there's the first level of these. So if the bases match, easy peasy, you'll be fine. But they're not always going to match. So what if the bases don't match? And I put the word yet here. What if the bases don't match yet? If they don't match right now, can I do a little rewriting to make them match? So you'll see some like that today on Delta Math. So let me pull up that and get a problem. So 16 to the x equals 4 to the 3x minus 1. Okay, so 16 to the x equals 4 to the, I think it was 3x minus 1. Okay, so there's my problem. So look at my bases. Got a 16, got a 4. Do they match? No, they don't. But is there a connection between a 16 and a 4? Can you think of any link between them? Yeah, 16 is 4 squared. So that's what I'm going to use here. I'm going to take this 16 and I'm going to rewrite that 16 as a 4 squared. I'm going to bring down my x, so that x is coming straight down. I'm just going to bring the right side down as well. 4 to the 3x minus 1. So if I look at the left side, I have a power to a power situation here. So because there would be like parentheses around that 4 squared. So what do you do when you have a power to a power with those exponents? You multiply. So this would be 4 to the 2x equals 4 to the 3x minus 1. Okay, they didn't start out as matching bases, but now I've converted them into matching bases. So now if the bases match, the exponents are going to have to also match. So technically the thing that we're doing here is we're saying I'm going to take the log base 4 of both sides. Since logarithms are the inverse operations of exponentiation, taking the log base 4 of a base of 4 cancels each other out. It's kind of like taking the square root of something that's squared, how it cancels each other out. Same thing is happening here. So it would just leave the 2x. Over on the right side, the log base 4 of 4 to the whatever, those would cancel each other out, and it would just leave the 3x minus 1. Okay, so now we're just down to a normal linear equation. So we can solve that. We could subtract 3x on both sides. So we'll get negative 1x equals negative 1. So if I divide both sides by negative 1, x equals, that would be a positive 1 because the two negatives would cancel. So x equals 1. Okay, so we first look to see if the bases match. If they do, great. It's not going to be a problem at all. If they don't, then we look and see, can I make them match somehow? Is there something I can do to convert them? But you won't always be able to do that. Sometimes they don't have anything in common. They don't have a similar link that you can use to rewrite it like we could with the 16 and the 4. So let me show you what to do with the next type. Let's see. Oh, okay. Let's show this first, and then I'll get to the more involved ones. So this, we have an exponential equation because my variable is up in the exponent. There's only one of them, so that's good. So let me write that down. 90 times 10 to the x over 4. 90 times 10 to the x over 4 equals, what was that? 76. Okay, I want to get that x by itself. Let me write it a little nicer. X over 4 is my exponent. Okay, so I want to solve for x. That's my goal here. Okay, so the x is divided by 4. It's up there in the exponent, so I'll have to get it out of there. And then that whole base of 10 to the x over 4 is all multiplied by 90. And then that result is equal to 76. So if I'm going to solve this, I need to peel the layers off in reverse. So let's make that 90 go away. It's getting multiplied. The link right here is multiplication. So how are you going to get rid of that? Yeah, you're going to divide. So we're going to divide both sides by 90. So I'll have 10 to the x over 4 equals 76 over 90. I'm just going to leave it like a fraction. If you wanted to reach for your calculator and divide that right now, you could. That'd be fine. So now I would like to take the log of both sides because I want to get it out of the exponent. So I'm going to use log base 10. Why do you think I'm choosing log base 10? Because the base is a 10. Yes. You know what? Even if the base wasn't a 10, you could use log base 10 because calculators can handle log base 10. So that's I'm gonna do here. I'm gonna take the log of both sides. So log. So remember, if I don't write the base as a subscript, you know I mean log base 10. But if it makes you feel better, we can write it in there real little. So log base 10 of 10 to the something, those two operations cancel each other out. So that's going to leave an x over 4 on the left side of my equation. So now I'm going to grab my calculator and I'm going to take log base 10 of 76 over 90. So log base 10 is just the log button. And then it opens a parentheses for me on this calculator. So I'm going to type in the 76 over 90 and close my parentheses. And I get a negative 0.07342817. Now, I wouldn't write that down. I wouldn't like round it as I write it down. I would just keep it right here on my calculator because I have one more step I need to do. If you notice, my x isn't by itself yet. It's still getting divided by that 4. So I need to get rid of that. How do you undo dividing by 4? You multiply by 4. So I'm going to multiply both sides by 4. On the left, they'll cancel, so x will equal. So the fact that I kept this on my calculator is good now, because now I can just hit times 4 and get my answer. Okay, now be real careful what you round to, because the directions will tell you how many place values to round to, and you need to watch that, okay? So let's say it said round to 3 decimal places. This would be a 294. That's what I would round that to. So there is that, solving that equation. Let's see what this would look like in a story problem. So this is my favorite part about exponentials, that they're very useful. So this one looks like it is about something decaying. Element X decays radioactively with a half-life of 6 minutes. There are 390 grams of element X. How long to the nearest minute would it take for the element to decay to 28 grams? Okay, so let's see here. I'm just going to take a picture of this and insert it real quick into my Smart Notebook so I can write on it. Maybe. Control V. Control V. Sorry, technical difficulties. Control V. There we go. Okay. Sorry about that. Let's make it okay, I guess I'm not going to make it bigger. Okay, so here we are. We have a half-life of 6 minutes. So that's where we are, or we're going to put that where, is that an H? That's an H down there. Because we're dividing the time into 6-minute chunks. So that's where the 6 is going to go. So I'm going to label this, that H is my 6. There's 390 grams to start with. So that's going to be my initial amount. So that's going to be my A value. And I want to know how much time it's going to take. So I'm looking for T. How much time it would take to get the element to decay to 28 grams. So that's what I want my output to be, is 28 grams. So that's going to make us have, let me fill everything in here. I'm going to replace the Y with the 28. The A I'm replacing with a 390 times 0.5 to the T over 6. Okay, so I filled everything in. So previously what I would have had you do is I would have had you take this information over to Desmos, and what we would have done is we would have typed in the equation y equals 390 times parentheses 0.5 to the parentheses x over 6. Oops, no extra parentheses there. Okay, so we would have graphed that. There it is. And then we would have said, okay, we want the output to be 28. So I would have added another line here and said y equals 28. So we would have something to look for. I'm not going to click on it yet, though, because I want to use this to verify in just a little bit that we can also solve this algebraically. So our variable is up in the exponent. It's getting divided by the 6. It's 0.5 to that, so it's been exponentiated, and then it's multiplied by the 390. So if we're going to reverse this stuff, we need to get rid of that 390 first. The bond is multiplication, so the way to break that bond is to divide. So we're going to divide on both sides by 390. Divide by 390. So there's the fairness at play. The 390s cancel on the right there. So I'm going to have 28 over 390 equals 0.5 to the t over 6. Okay. I need a clean page. It's fine. So now I want to get this out of the exponent. So the opposite of exponentiation is taking the logarithm. So I'm going to take the logarithm of both sides. So now you might be thinking, well, the base that I see is a 0.5, so you should use a base of 0.5. You can if you're going to use a calculator that can handle that, which would be like the Desmos calculator. I just feel like using this one right here, though, and this calculator can do natural logs and log base 10s. So I'm going to use one of those. I feel like using log base 10. So that's what I'm going to do. And I do want a fresh page for this. It's too messy. So 28 over 390 equals, what was it? It was 0.5 to the t over 6. So I'm going to take the log of both sides right now. We have to be fair and do this on both sides. So I'm taking the log. You can see the fairness in the red, that I'm doing that on both sides. If it makes you feel better, you can write the base 10 here. You can squeeze it in. So I'm going to see what this comes out to on the left side. So let me grab my calculator. So log of 28 divided by 390, close my parentheses. That comes out to negative 1.14390. There's lots of digits. I'm going to keep it on my calculator. I'll write down an approximation of it, but I'm keeping it on here to keep it accurate, okay? Now, on the right side of this equation, I still have my t over 6 up in the spot of an exponent. So using the power to a power property, I'm going to shift that out front of my logarithm. It's going to be t over 6 times log base 10 of the 0.5. What that does is that gives me something I can evaluate on my calculator. There's no variables in that part that I just underlined, so I can calculate that. Oh, it means I have to clear this off for a little bit. Darn it. Okay, so log base 10 of a 0.5 is negative 0.30. Okay, so I have t over 6 times negative 0.3010299996 equals, I'm going to bring down this number, oh, I should show you another way to do this. I'll do that in a minute. Okay, so I need to take these, if I want to get rid of this multiplying by this big number, I need to divide by that big number. 0.1029996. I'm going to divide it over here. 0.3010299996. So that means on the right side we still have the t over 6 because those cancel, but I still have that t over 6. This is going to be divided by 3.7999 0.768. Now your t is over a 6, so to get rid of the fact that it's getting divided by 6, I need to multiply by 6 on both sides. I'll multiply both sides by 6. Those will cancel. So t equals, I'm going to multiply by 6, and I get 22. It's about 22.8. Watch what it says to round to in the directions, all right? I don't know what this direction said to round to, but it's about 22.7998. So watch and round accurately before you put your decimal in. Okay, so there's that. Halfway through, I realized I should have shown you how to do this, not touching your calculator until the end. So let me go back up to right here. I'm going to get rid of this part. I didn't do anything wrong. I just had to write a lot of digits, and that was getting tiresome, so here's another thought. So instead of reaching for my calculator, I'm just going to write this down. I'm going to write down the log of 28 over 390. I'm going to bring that t over 6 out front, times log of a 0.5. So if I want to get rid of the multiplying of the log, I need to divide by the log. So instead of evaluating it at the not beginning, but in the middle here, I'm just going to leave it written in log form for a minute. It's easier to write that than all of those digits. So let me clean this up. So on the right side, I have t over 6. On the left side, I have the log. I feel like I wrote something down wrong. Did I? That's a 390. Oh my goodness. 390. Log of 28 over 390. Divided by the log of 0.5. Okay, now focus on your t over here, because that's what we're trying to get by itself. What's keeping that t from being by itself? The divided by 6. That's what we want to get rid of right now, so I'm going to multiply on both sides by 6. You can think of it as a 6 over 1 if you wanted, so I can just put the 6 up with the numerator. That 1, I don't really need it. It's not going to change anything if I multiply by that 1. On the right side, these are going to cancel, so my t will be by itself. Then I can reach for my calculator and evaluate that stuff. So I'm going to type in 6 times the log of 28 over 390. Make sure I close that parentheses. And then I'm going to divide that by the log of 0.5. And I got the exact same answer that I got a little bit ago. So either way is okay. Just if you don't like having to write down a whole bunch of digits and that's annoying to you, you can wait to take the logarithm until the end. Oh yeah, I was going to show you how that verifies on the graph. So if you look over here, we previously had solved these by just looking for that target output, 28 in this case, and then finding where those two intersect. And look at that. Do you see how the x value is 28 or 22.8? And that's what our calculation yielded as well. So the graph verifies our algebraic solution. So that's good news. Phew. So, all right, so that's what we're doing today, is solving exponential equations. So remember that Jesus loves you, and so do I. So do your math.